Any questions on math instructions? Everybody okay? We are going to have to make a little modifications. I think I did it at the very first of the lab procedures, or at the lab that's required. We say that every lab that we're going to do, you just get used to this, is to have some way to turn the whole thing on or turn the whole thing off. We usually refer to this as start, stop, station, reset, or whatever. But I just call mine start, stop. So what we would do is, if we're going to turn the whole thing off, is, and we got a little problem with this, in that when we come up here and originally load the program, we're using N7, or it doesn't make any difference which one we're using. When we originally load up the software, or the application the first time, what we end up with is we end up with zeros in our registers. So what happens, as soon as the program goes to run, it faults, and it's a major fault. And what's the problem? Yeah, because what we're doing is we're dividing these two. We're dividing N7 0, 0, and N7 1. We're dividing those two numbers, and any number divided by 0 is what? Infinity, right? You understand? So what was happening was, as soon as the program came up, it faulted just like that. And then you could clear the fault, and it would switch down to program mode, because it would fault again. But every time you switched back to run mode, it would do what? Fault. One of the things that we could do was to come in and enter numbers into the N7 register before we start off with just any number, and you wouldn't even have to enter it in 0. All you have to do is just put a number in 1, but we don't need to do that, because you wouldn't do that in real life anyway, right? So what we're doing is we're going to put a start-stop station, and what we're going to do with the start-stop station is we're just going to put and we're going to use one of our B files, right? You understand? Because we don't want to sacrifice an output for something that's totally inside a program. So B3, we got 256 B3 bits that we can use. By the way, later on, we're going to deal with instructions that also use this bit file. We're going to use it for other things besides internal relays. And we'll show y'all, of course, that would be where it becomes advantageous to be able to set up another bit file, right? Does that make sense? And then you can use one of them for your internal contact or your internal relays, and also for the other instructions we're going to deal with. So what I've done is I've left the move instruction alone, because I want to be able to move something into those into these registers before I tell it to work. So what we would do, the way the program will work, is we'll go ahead and put something in these registers. So right now I've got 35 and 36, right? You understand? And then what can I do? Well, I can come over here and I can hit switch 2. Yeah. Oh, I'm not online, sorry. Yeah, I downloaded it, I think. We'll check and see. And then we should be able to do what? We should be able to run the program if it goes online. Okay. It says it couldn't define the processor. Wait a second, let me see if it got switched off accidentally with my foot. It did. So it got switched off. So I got to watch my foot under here. So I lost my IP address. So what do I need to do? You know, so we'll run this DHCP tool that comes with RSLogic software. It even comes with the RSLogic 5000 software too. So this is, even if you get a a newer, like a Compact Logix PLC, this would be the first thing you would do before you communicated with it, is set up an IP, right? Okay. And you got to know the MAC address. So this is the MAC address. You can see the MAC address. I don't know if I can pick this up on my camera or not. Yeah. It was show went out there and started finding things that was asked IP. The latest TCP/IP protocol works. If you have it set up for what we call dynamic IP, as soon as you turn that device on, it asks for an IP address. And then it asks for an IP address it says, hey, is there a DHCP server, which is a dynamic host configuration protocol server? If it doesn't find one, then nothing happens. It won't get an IP address. If it does find one, then it'll say I'm here, and it says, okay, I need an IP address. But you're right. IP stands for Internet Protocol. And so what you can do is somehow on the Compact Logix, the MAC address is written on there. When you open up the door to the CPU, the MAC address is actually written on there. But you got to know the MAC address. Why? Because you don't know which. Yeah. Well, you don't know what. So we got two that's asking for one. We got the 843A. I don't know who that is, but it asked for one. And if I would have signed that one, it wouldn't done any good. So you need to know the MAC address of the device. On the 1100s, what you do is you go through the menu, and y'all just come up here. So that way I won't have to get my camera. There's two parts to an IP address. First of all, you got to understand there could be millions of computers on a network, right? So what we do on an IP address is divided into two different parts. So it's a 48-bit number, but they understand that you don't understand 48 bits, right? So they give it to you in hexadecimal, and then they split it into 4-bit groups. That would be 8-bit groups, so that would be bytes, right? Each one of those are hex, so each one of them represents a nibble or 4 binary bits. Y'all remember all this, right? So what they do is the first 24 bits is what we call the manufacturer's ID, and the next 24 bits would be the 24 bits that manufacturer would use. So usually when you get a PLC, you'll find out right off the bat what the most significant word is, and then after that it should be okay, right? But if you're doing like James says, multiple IPs, then what do you got to do? You need to go to all your machines and get the IP address on there. Well, when we get into the IP address is divided into two parts. The two parts that it's divided into is what we call a subnet mask. A subnet ID, which would identify the network that the IP network that the device is connected to, and then we have a node, what they call a node address, which would be the actual device itself. Does that make sense? Well, what you have to do is we have these things called routers. So routers, what they basically do is they basically look at the subnet address, right? You understand, to decide which route it's supposed to send you into, to which route your computer's on. And y'all have heard routers, right? And so that's what it does. It deals with it. But we have to identify what part of the IP address and what part of the IP address and what part of the IP address is the subnet, and what part of the IP is what we call the node address. So we use a thing called a subnet mask. Have you ever heard of that? Yeah. Well, the problem is when you're using dynamic IPs, everything is assigned for you. Everything's assigned for you. It takes care of everything for you. Your DHCP server knows where your gateway's at. Your DHCP server knows where your DNS servers are at. Yeah, it's on the DHCP server. So that's what's nice about dynamic IPs, is that they do everything for you. But if you got something that you don't want to move around, the problem with with dynamic IP addresses is they're leased for a certain amount of time. And what that means, technically, what that means is that when you log into your internet service provider, they give you an IP address, and as soon as you log off, that IP address is free again. And the next time you log in, you'll get another IP address, right? You understand? So your IP addresses are constantly floating around. Our DHCP server here has this like a 2-week. It's got a 2-week lease. So that means if our computer is off for 2 weeks, then what happens? Well, when we come back, our IP would be different, right? So they float around. Now, internet IPs, those are static. So the college pays for internet IPs. We don't get those for free. We pay for them. 207.157.something.something. So we pay for 3, I think, of internet IPs. Those are out on the internet. Then we have what we call private IPs. These are IPs that are never intended to get out on the internet. So if you looked at the IP address on your computer, even on when you was at your house and you connected to your wireless on there, you would get a private IP, and it would be like a 169 or a 172 or something like that, depending what subnet mask you use. So if you go into here, and you actually look at your network, and then you go to adapter settings, and then here's our adapter. This is on the wired. Yeah, and then properties. So you got 2 options here, and then we're using the TCP/IP4 protocol. And you got 2 options. You can set it up for what? Right here. Obtain an IP address what? Automatically. Or you can do what? Yeah, you have, if you come up here and click on that button right there, then you're setting up this device for what we call static IPs, which means you have to assign the IP, you have to assign the subnet mask, you have to identify the gateways, right? You have to identify the DNS servers. Y'all know what DNS servers are? Dynamic naming service. It's a dynamic naming service. So what do we use? Do you know the IP address of any of the internet sites you go to? What do you know? You know a URL, or you know a name. Well, that's what the DNS server does. That's what it goes to. So when you put like a .com or a .edu or a like that, you're identifying a big DNS server out there that basically matches IPs to names. So what happens when you type in that name and you put .com, it goes to a .com DNS servers, and it's like the contact list on your phone. So it does exactly, that's what a DNS server does. It matches a what? A name to a IP address. So it's doing, that's what DNS servers does, exactly the same thing. So you can do your DNS server static. So you can do your DNS server static, and you can still get your IP. Now, what's the gateway? Anybody know what a gateway is? It's a protocol converter. It literally, so Wi-Fi is what we call baseband. The internet is what we call broadband. I could not connect this computer using baseband into the internet that uses broadband. So what do we have to go to get to the internet? You got to go through a gateway. It's just that your router's got the gateway built into it. Routers don't do that. What routers does, it allows us to take an extremely big network and break it down into subnets. That's what it does. It allows us to break it down into subnets. And in that way, you're not all fighting on a baseband network. You're not all fighting for time, because as long as you're on your subnet, then you're not broadcasting over your whole network, right? Does that make sense? Yeah. So a gateway converts protocols. So these are very, very important. So if you go to the internet, odds are you're going to go through a what? You're going to go through a gateway. Huh? Well, it's still broadband, but people, what happens when they go in and have that denial of service is just they get thousands of robot computers try to access that website at the same time. So a lot of people don't know that their computers they've installed some like a spyware, not spyware. That's I forgot this guy. They all got names, but a lot of times it'll install that stuff on your computer and you never know it. Yeah, I don't know I don't know. I need to look that up. But what it does, it makes your computer do what? Certain time, not your computer. It's just you never even know it. It's just that it starts acting. They send out a command and it starts. So these guys that's doing this, they don't have thousands of computers. They're using your computer. So they tell your computer to broadcast that because you've installed that. I guess it would be malware, and you never even know it. So that's why you need to have a good virus checker on your computers. Keep that from happening. There's a lot of people out there that don't do that though. So what we have to do to make sure that this computer this PLC can communicate with this computer is I have to put it in the same subnet. Does that make sense? Okay. So when I bring this up, I'm just looking. Here's the IP for my network card. It's a private IP. It's a Class B IP. So I think I get those confused. It's either Class C or Class B. Class A would use a subnet mask of but people, you have to know binary to figure out subnet mask. So let me do this one. So how many bits is an IP address? IPv4 is a 32-bit IP address, and then IPv6 is no, it's huge. I have to go look up. So what they do to make IP addresses make sense to us is they do it in what we call a dotted quad. So they do it in decimal, but they split it up into bytes. And then they convert each one of them to a decimal number. That's why if you ever enter like 256, it's going to say that's invalid because the biggest thing you could possibly have with 8 bits is 255, right? Understand? So you'll never see an IP address that's over what? 250, yeah, 255, yeah. And if you enter one, you're going to get an error right off the bat. Each letter is a byte. No, each number is a byte. So what they do is so y'all understand that now? So they display it in decimal for you, and they take it up and set it up into 4 bytes, right? You understand? And that's the decimal number. So 169 would actually be whatever the actual IP address would be, whatever binary number that was 169. So you don't put out a 169 when you go out the internet. You put out that 32-bit binary number. That's what's in the header of the IP. Of the packet. So yeah, but they understand, those computers understand that most people don't understand binary, so they do a lot of stuff in decimal for us. that 32? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Get 2 minutes. So this would be an IP address, 32 bits. But they don't, yeah, that's an IP address, 32 bits. But they do it like this. Like this, it said 169, and then was it 253, and then they'd have another number like here, like 82, and then 10. And then they separate it by what? By dots. And we call it a dotted quad. And they display it in decimal to us. Why? Because if they displayed that sucker in 32-bit binary, nobody would understand IP addresses. And remember, computers can make things appear like they're not really, because all they're doing when they display on something on the screen is turning on dots. Right? You understand that? So the subnet mask, what we would do in the subnet mask, if we wanted to identify the network ID, we would put all ones in the subnet mask. And then if we wanted to identify the actual node, then we put zeros in the subnet mask. Now, the way we would enter this is we would enter it 255.255.0.0, and that would be the subnet mask for this. We call this a Class B subnet. So a Class B subnet Class B network uses 16 bits, which means I could have 65,536 computers on a subnet. A Class C, it's a Class C subnet mask is 255.255.255.0. So if you had a Class C network, it would come up and give you you could have 255 computers on a subnet by itself. But you could have another subnet and have 255 more computers, and another subnet and have a 255 more computers. Does that make sense? A Class A subnet mask is 255.0.0.0. So we could have 2 to the 24th, whatever that is, 2 to the 24th computers on that. So we're running for some reason, I don't have the slightest idea. When you log into the wireless network, it's 10.10. If you looked at the address, it's 10.10. That's a Class A subnet. That's a Class A network. So literally, they could have a couple of billion of computers on that subnet without dividing it out. So if I'm using this one, so 169 is a Class B. So that means when I enter my network, when I enter my IP address for my PLC, I've got to enter these right here exactly the same as my computer. If they're not the same, then it's going to think they're on a different subnet, and they won't do what? It won't communicate with each other, because you're saying, okay, my computer's over here on this subnet, and this guy's over here on this subnet. So so one thing you need to know is you need to know the IP address of your computer, right? You understand that? And how can you find that out? Huh? Command prompt, yeah. So it's command prompt. This is still, it's even available on Windows 10. It's not easy to find, but Windows 10, well, it is easy to find because Windows 10 has got that little search box down the bottom. You just type in command prompt, it'll pop up just like that. Yeah, if you got, yeah. And then I usually, if I'm gonna do with it a lot, I actually pin it to the taskbar. And the command is config. And I'm sorry, wrong thing. IP config. Can y'all see that? And this is going to pop up all your IP addresses in your. If you come up and put /all, guys, this is going to tell you everything about. It's going to tell you your MAC addresses. It's going to tell you your. It's going to tell you the DNS servers that it's set up for. It's going to tell you everything about those things. /all. So 172.25, this is the ones that that our DHCP server assigns. And then it shows you subnet mask. It shows you the subnet mask 255.255.224. Well, what it means is this right here. We can figure out how many computers. Now, it don't mean anything if you can't convert that to what? Binary. Don't mean anything. But to figure out how this thing is split up, and so if you're going to do networking, you're going to have to understand binary number system. And if you're going to play around with the TCP, the TCP IP, the TCP is how it puts packets together. So when you get on the internet or when you go to a device, you don't get, if you're transferring 100 megabytes, you don't get 100 megabytes worth of bandwidth. You just your information is split up into packets. You transmit a packet, then you free it up. You transmit a packet, you free it up, right? You understand? So everything's done in packets. TCP/IP, which is the transfer control protocol, that defines how the packets are put together. The PLCs, they use what they call a CPS packet, which it still transfers over an Ethernet network, but it's got stuff in there that actually handles control information, right? Control process. I don't know what else. This guy shows you everything. So you'd come up here. If you don't want to see everything, you'd just use IP config, and then we'll drop down here 169.254.163.226. And it's using the subnet mask of this. Can y'all see the subnet mask? So this is what we call a class B. And most of the time, when you use that, your computer will automatically pop that 255.255.0.0 in there because it knows that 169 is a class B. Okay? So, y'all got that written down? Of course, we don't need that. I'll show you. Sometimes this happens and sometimes it don't, and I don't know why. What this guy has done for me is it's given me the IP address up in the very top. But for every once in a while, when I run DHCP, this DHCP server, it don't give me the IP of my computer. It just did at that time, so that's neat. So I'm going to start off doing what? 169. That's got to be the same. If I give it a different, it's going to put it where? It's going to put it in a different what? Subnet, right? 254. By the way, you can assign this yourself too. I'm going to go ahead and put 163, even though that don't have to be the same, because this is the one I've been using. Because why do you need this? Well, this information is actually saved in your program. So that means if you change your IP address, your program might not work. And then I'll go OK. And as soon as it pops up here, then that should take care of it for us. So if I knew the address of my if I wanted to reassign the IP address on my network card, you could use I'm gonna come up here and say IP config. And I'm going to put /?. And what this will do for any command prompt, what it'll do is it'll come up here and tell you the available options. So one thing I can do is I can come up here and I can do what? I can release the IP. So if I released it, then my computer's going to ask for another one, right? You understand? Does that make sense? So if I've got all my IPs and I look at that thing and it's got a weird IP address, and I could assign it to the subnet for the PLC that I've got. But see, I did that. So we could renew it. If I hit renew, then it's going to go out and ask my DHCP server for a new IP address. And of course, all of them display everything. So guys, if you're going to deal with the TCP/IP protocol, you're going to have to learn how to use command prompt. And that's why it's still part of Windows, even though Windows 10. This is what we saw. This was DOS. Command prompt was DOS. So when you booted up, you saw this little thing right here. We call that a cursor because that's what you felt like doing sometimes. And it was just waiting on you to do what? Type in a command. So you had to learn all these commands, and you had to learn all the syntax for the commands. So about the only time we use this now is for is to control you can do a trace circuit too. I need to show you that. So you can see the IP addresses that your computer goes to get from you to wherever you're going to. It's really cool too. So y'all might, if you want to play around with it, you can look up the TCP commands, prompts, and there's a lot of them. Okay, so it got it, right? I'm going to double check it's there, so we should be able to. So anytime your PLC says that, what does that mean? It says, I'm unable to communicate with your PLC. What could be wrong? Well, it could have lost its what? Could have lost its IP for some reason, right? Or your cable that you got connected up might be wrong. Unfortunately, the new compact logics, you can't go in and see the IP that's actually there. It shows you the MAC address. So y'all learned a little bit about networking, right? So let's see if this works now. So here, we'll go up here to comms, see who's active. Yeah. Well, not in an integer, because that way you won't have to worry about overflow, right? So N9 is a watt. So L is a watt. Yeah, which means it's what? 32 bits, right? But remember, we only get 31 bits of that. Yeah. Well, you can, yeah, you're going to have to go to different L registers, right? And why? Because if you go to the same one, yeah. By the way, and we had this happen a couple of times already, is that you cannot duplicate, normally, you cannot duplicate output addresses, right? You understand that? So this has happened a couple of times where I got called back there and they say, well, the rung's true, but the output don't go true. And what's been wrong both times? They had that same output down here. So this rung up here was false. This rung down here was what? I mean, true. So your computer don't know what to do with it. So be careful on that. When can we use duplicate addresses? Output addresses. We could do it if you repeat the rung exactly. That's legal, right? Now the problem is that if you duplicate IO output addresses, it's not going to tell you that it's bad when you check it because it compiles over correctly, right? Or you can duplicate it with latch and unlatch. So at latch and unlatch, you duplicate duplicate that, but you can't. And why? Because you can't latch and unlatch at the same time, right? That makes sense. So there's my PLC. I'm okay. So we'll go ahead and download it. And download too. We had was that you and Jalen that hit upload? And when you upload, what's it going to do? It's going to bring it from the PLC. What happens to your program? So in upload, don't give you time to save, right? So what I can do now, though, is I can come up here. Didn't get an error when it switched to run. Why? Because the divide down here is not what? It's not enabled, right? Okay. So I can load my numbers. I'm going to switch to. Okay, so I just loaded my numbers, right? You understand? And then what can I do? I've got to wait, switch 0. It's got to be on all the time. And then I could come up here and hit that, and notice I didn't get an error. And it did the math, right? Everybody understand that? So this is the way you're going to have to basically modify your program. Now, I didn't want to put my move inside my enable because if I tried to move and enable at the same time, I would probably get a fault too. Are we okay? This makes sense? And what we're going to do, mine's still a little different. This is O. We're going to make sure we store down here your destination. You want these to be what? L register. Yeah, L. Yeah. And down here for your divide, you're going to use an F8 because why? Because you're going, in case you get a fraction, right? Everybody okay? Now notice it didn't shift into engineer or scientific notation because you haven't exceeded that range before it shifts into it, right? Oh, was you going to take a picture of that? You got it. So this is pretty straightforward. It's a lot easier than the timer counter thing that y'all ran into first time, right? Yeah. Yeah, and we're doing 2 move instructions to load. This is going to be our top number. This is going to be our bottom number, right? Okay. Yeah, but you got to do it, and we still can't do it dynamically. No, because as soon as you run that, we could do it that way. No, because this is a constant. And so what would happen as soon as I close that switch, it would take this number right here. And see, oh yeah, Willow's changed that number. No, we can't change it. We can change it, but the problem is if I touch this thing right here, it'll go back to the original thing. I'm almost sure. So we can change this guy down here, right? And then the math should have responded instantly. So did it? No, it didn't change. It looked like it did. So 56. No, it won't change. So it won't let you dynamically change it. So what we'll have to do is we'll have to set up the numbers before you run the program. Any more questions? So you're going to have one rung for add, you're going to have one rung for subtract, you're going to have one rung for multiply, one rung for divide. Right? So what's the next chapter? Compare and jump. Can't remember that. I think on my PowerPoints it's on the next line. So the test will just go through compare instructions. I don't think it's got MCR on there. I'll have to go back and look at the review. Yeah, it looks like compare. Looks like MCRs are in here too. So what do we want to do when we compare? First of all, how many operands is compare is going to work on? 2, right? And what do we want to do when we compare? When we compare 2 numbers, what do we want to know about numbers? That would be subtraction, but what we would know if I had 2, if what? No, that's math. We're talking about compare instruction. I'm comparing 2 numbers. What would we want to know about 2 numbers if we're comparing 2 numbers? If they're the same, or if they're equal to each other, right? We would want to know if they're equal to each other. What else would we want to know? You went through all this in math, guys. Well, that would be subtraction. We can't do that with compare instructions. So what y'all learn in math? Yeah, all them different symbols you learned in math. Equal to, greater than, equal to. Didn't y'all go through all that garbage? This is what we do with compares. We're going to tell if two numbers are what? Equal. We're going to tell if they're not equal, which one's greater, which one's less, right? You understand? So we're going to be able to do that, right? So these are all our compare instructions. This is the power that there's no way in the world I can do this with relay logic. Every programming language that I've ever programmed in, and I program in a lot, they all have these instructions. Most programming languages calls them if-then, if-then, if this equals to this and not equal to that. But this guy, we actually can put it in a block. Yeah, and what I'm saying is that how many timers did you use on your program right now? On the program that you're doing right now, your timer counter. You could have done it using these commands right here. You could have done it with one timer. One timer. Could have done it with one timer. So that reversing circuit back there that runs a certain amount of time, stops for a certain amount of time, reverses, that's done with one timer. That I hooked up and showed y'all last semester. One timer. And I'll show y'all that program. So we're okay on our files, right? Unfortunately, as soon as you get into Siemens or Step 7 software, or as soon as you get into 5000, all this is out the window. And why is that? So what's the problem with this right here? But what if you don't use any control registers? Well, you still lost all the bytes of your memory. What if you're not using any math? Well, you've lost all this memory right here. What if you're not losing any floating point, which is basically 3 bytes? You lose all this memory just for something you don't use. So what on your new PLCs, they don't assign the memory to anything. The memory is assigned when you use it, right? You understand that? So, but it's a lot the same. It's just that's one big difference. We talked about the L file, right? So the L file, if we use the L to store our numbers, that means I don't have to worry about exceeding the range of the math. So our math range, if we're using 16-bit numbers, what's the range of our math? When I add a number, what's the biggest thing I could possibly have? What answer could I possibly have? It's 16-bit. No, I could have 32,000. I could have a positive 32,766. That's the maximum I did because we're doing, huh? Wait a minute. They're integers. We're using integers, signed integers, right? Y'all understand that in register, signed register, that in register, the maximum positive number you could probably have would be what? 32,767 positive or 768 negative, right? Period. Okay. So we could easily exceed the range of these math operations. But if I'm taking my destination as an L register, then that's where it's going to put the answer, right? Now we can go all the way up to what? 2,147,482,647 integers. If you use L file for your destination, right? If you don't use your L file, you're going to have to be real careful on your answer because that's what the destination is. It's the answer, right? You understand? So that's why you don't need to use L files for your source A and source B. But make sure you use an L file for your what? For your answer. Except for division. Why can't you use an L file for a division? Yeah, because even if I use the L file, I would lose my fraction, right? Compare instructions, energize coil. Well, actually, energize output instructions. Compare instructions are input instructions. So that means they're going to go on the left of the rung. They'll go between L1 and output, right? Output instructions. Cascade compares. They call it cascade, but it's going to be a little different. We can hook them in what? Series, because it's an input instruction. How many input instructions can you put in series? Or parallel, you can put them any way you want to, right? You understand that? We'll use a jump instruction. What does jump instruction do for us? Yeah, let's actually skip overruns. We can actually change the sequence of the program. And we can use multiple jump instructions going to the same. We actually call it jump to label. So anytime you say jump, you have to say where, right? You understand? So what we do is we use what we call a label instruction to go to where, indicate where we want to go to. By the way, these are even available on robots. What, these PowerPoints? Yeah. I think there's been some, I made some modifications on them today. I'll try to get the newest version. Well, you could, right? And the jump instructions can be what we call conditional or unconditional. We'll talk about that when we get there. So you could use them for troubleshooting. So you could literally go into your PLC program and deliberately skip over some rungs if you wanted to. And then the MCR is what we usually use for e-stops. So we'll talk about this. So here we go, guys. Equal to. So A is equal to B. So we're going to have a source A and a source B, right? A is equal to B. Then we can check to see if they're what? Not equal. We can check to see if A is less than B. We can check to see if A is greater than B, right? We can see if what? A is less than or equal to B. We can see if A is greater than or equal to B. So these are our compare instructions. Are we okay? Any questions? Yeah, this is right out of the book. Questions? We okay? So these are where our operating come from. Source A, we can get them from an output. We can get them from an output data file. We can get them from an input data file. We can get them from the status. We can get them from a bit file. We can get them from a timer. We can get them from a counter. We can get them from a register. We can get them from the N file. We can get them from the L file. We can get them from the L file. The source cannot use immediate addressing. So A cannot be a constant. So that's got to come from somewhere, right? And both of them can't be constants. That should be there somewhere. So that should be in the book. So that if you put constants for both of them, it would either always be what? False, or it always would be true. So, in fact, that will give you an error. For the source, we can use immediate addressing or direct address, and we can use indirect, which we hadn't got into right yet. So what's immediate addressing? What is immediate addressing? Yeah, it's a constant. So that means the actual operand is in part of the instruction, right? Okay. And what's direct? Yeah, it's the address of where the operand is located at, right? Everybody okay? So when you say that N7 and that stuff in your math instruction, you're using direct address. So we're probably going to get ours from one of these registers right here, right? Well, we could get it from inputs. Immediate addressing, the actual operand is part of the instruction. Direct addressing, the operand is located in the specified data file. And there's a lot of them, right? So here we use this N7:0. That means the operand would be located in the integer data file in address 0. Indirect, the specified data file address contains the word address of the operand within the data file. So if we said, now notice how you identify direct addressing. You put what around it? Yeah, brackets. And I say N7:1. Well, what it would do is it would go to N7:1, and in my example, I have 15 there. So the actual operand would be N7:15. That makes sense? Good. Yeah, this is indirect. So we're getting the address of the operand indirectly through the register, right? So the only two that we're dealing with right now is immediate and direct, right? Everybody okay on those? Because we've already used them, right? When the PLC is scanning ladder diagrams, sometimes one or more rung needs to be scanned. When the rung is not scanned, the state of the instructions on the rung remains the same. And then conditions for skipping over runs can be generated by either state of input or contact. I don't know if it's compare instructions. What they're saying is that if you use the jump instruction, if you jump over rungs, you can press the input button as many times as you want to. It's not going to be what? It's not going to be honored, right? That makes sense. And the outputs will stay exactly what they were. So here's a equal to. It's an input instruction. It goes over on the what? Left. So what am I saying here? I'm saying if source A and source B are equal to each other, this rung would become true. If source A and source B are not equal to each other, this rung would be false. Does this make sense? Pretty straightforward. Very powerful command. This is not equal to. So that means if source A and source B are not equal, now source A, it's got to be an address. Source B can be an operand. It could use immediate, or it could use one of the other addressing modes. Right now we're using direct, right? We're in these examples we're using integer files. Where could this come from? It could come from, right? So we could compare and say, okay, if my input port is equal to this, then do something. Right? Does that make sense? Or if we could say our outputs are in this situation, we could use the bit files. So bit files can be used for a lot of things. So if they're not equal, the rung will be true, right? If they are equal, the rung will be what? False. Everybody okay on that one? Less than. So that means if A is less than B, the rung would be true. If A is greater than B, the rung would be false. Source A must be a supported data file address. Source B can be either an address or a number. By the way, the book incorrectly, yeah, this is out of the book. The guy, yeah, so you could do math, and then you could say, well, I want to know if my answer, for some reason, I want to know if my answer here and my answer down here are the same, right? Understand? Yeah. Well, you could do certain things. So you could say, if you're in manufacturing, you say, okay, I'm counting cans to come by, and in every 5 cans I want to do this, every 4 cans I want to do that, right? So you run it through your counter. You said, okay, if it's equal to 5, then do this. If it's equal to 10, do this, right? You understand? The jump instruction, we could come up here and say, okay, I've got 2 different boxes, right? One of them, I'm going to put 6 devices in. I'm going to put 12 devices in. Well, you could flip a switch and say, okay, jump over these that does 6 and do the 12, or jump over the 12 and do the 6, right? So these are really uh, on robots. If you're in robots operation and programming, that's you have to use a jump to make it do what? To make the program loop. Yeah, to make it loop. So these guys don't loop automatically. So these programs loop automatically. So that means when it hits the end, what does it do? It automatically loops. Robots don't do that. Robots, if you want it to loop, you have to do what? You have to put the jump or go to. They either call it the jump or they call it go to. But they're the same thing. It's just a different. In fact, the PLCs might call it a little different. But do y'all understand this one? Everybody okay? Speak out or forever hold your peace, right? So wherever A is coming from, let's say A is 53 and B is 39. Would this rung be true or false? Yeah, now this era, so it's less than. So when we talk about less than or equal to, we're talking about A. A is what we're looking at, right? A is the first one. So we're saying A has to be less than B. Well, A is what? More. Yeah, so this rung would be false. That makes sense? We okay? But if I swap the numbers, the rung would have been what? True. Greater than, so we're saying if A is greater than B. So you notice the arrow always points toward the smaller one, right? A lot of people get that confused. If A is greater than B. Some teachers teach that. Because it's got more meat on it, right? So if this was 53 and this was 39 again, would this be true or false? Yeah, this would be true, right? Good. And so what would happen over here? Then whatever's over there would become true, right? We're using output instructions. This could be an add instruction over here. So if we say, okay, if this is greater than this, then add these two numbers together. So any output instruction can be controlled by these. And the only output instructions we looked at so far is bit files, right? And then true outputs, and then our timers, counters. Less than or equal to. So that means if this was 53 and this was 53, this guy would be what? They would be equal. This would be true. If this was 53 and this was 39, now make it false. Good. Are we okay? Everybody okay? Greater than or equal to. So we're saying if A is greater than or equal to B, so if I had 53, 53, it'd be true, right? If I had 53, 39, it would still be true, right? Everybody okay? Yes, no? Well, yeah, so equal, greater than or equal. So we're saying A, so A is the guy on the front, right? If A is greater than or equal to B. So if I did like 39 and 39, greater than or equal to, it would be what? It'd be true, right? If I came over here and said 53 and 32, it would be what? It'd be true, yeah. If I came over here and said 32 and 57, it would be what? Greater than. Yeah, false. Yeah, I got y'all, didn't I? This is not in the book, but this is we can combine greater. We can combine or put them in series to actually create a range. So we could come up here greater than, so we say this guy's got to be, let's say this is 53, and then this right here. So we have to put the small one on the greater than or less than. Would this ever work? Is this the book? Is this in your book? Oh, it's a Logic Pro. Yeah, it would work. So how would this work? So I'm putting numbers up here. That would be where we get that from. Remember, source A has got to be a data file, right? So when would the counter be enabled? When would it count? So when would the first one become true? When would the first one become true? No, this is the number we're comparing to. This is oh, I'm sorry. So you're right. I didn't see those two numbers. Thank you. So what range of numbers would this let through? No, you can't say anything over 100. Because I could put 163 and it wouldn't get through. Okay, so anything over 100. Okay, so let's say I had 192. Well, this right here would be true. But this says it's got to be less than or equal to what? 150. So this right here would be what? False. So the rung would be false. 101, right? Now this says what? Less than 100, 149. You're exactly right. So this will let any number between that range do what? Go through. So what we've done is we've set a range of numbers we can get through. Are we okay? Questions? We do this a lot. Yeah, I understand. So back there, when I run my motor, this is basically what I'm doing. I'm saying run it forward. I got one timer. I'm saying run it forward when the timer's between this range. When it gets out of that range, it drops out, right? Then I run it to another timer that I say okay. Then I run it to another one that says what? When it's between this range, reverse it. So y'all remember the program? Y'all probably don't. I know Scott don't. I'll hook that up and run it again. So what would this program do? Figure 11-1. Is this chapter 11? Okay. Yeah. So is this in the book? No, this is actually programmed in. I've got this somewhere. The figure might be wrong. The programs on Logic Pro was actually set up on an older version. The source is a counter. So we got a counter that can count from 0 to 20. It's an up. Well, that's not true. How far can a counter count? How far can a counter count? How far can a counter count? That's how many counters we can have. How far can a counter count? 32. Yeah, it could count 32,000. Yeah, 32,767. And then if we make it go past that, what's going to happen? It's going to change. The signs are going to change. But we know after 20, the done bit's going to be set, right? Okay. And of course, how far can this counter count? It looks like it's going to be able to count to 19. Can y'all see why? Yeah, it resets on 20. Y'all see this? So down here. So as soon as C5 is done, which is going to be done on 20, it would reset itself. So we'd never see 20. Okay, so what's going to happen? I'll start my counter counting. So what's going to happen? If I got 1, what's going to happen? So here we're setting a range. What's our range down here? 5 to what? This says greater than or equal to. So this was a little different than the other one, greater than or equal to. So that means this guy would be true if it was between the range of what? 5 and 10. Okay. This says equal to. So when then this is going to be true. This is going to only be equal to what? When it's 10. This guy right here is going to be true anytime it's greater than 10, right? So we start off counting 1. What's going to happen? Nothing. 2, 3, 4, 5. This goes true. Less than 10. This goes what? True. So that means whatever we hit, the white pilot light should come on. Right. 7, 8, 9, 10. Yeah, this guy right here will go what? True. Right. So that means our green pilot light will go on. 11, 12, 13, 14. Huh? So this guy's gonna so this guy's gonna go what? I'm sorry, y'all was right. This guy's gonna go what? As soon as this hits 11, this is gonna go what? False. Yeah, good. And then this right here would be, as soon as this goes 10, this guy here will go true, and it'll stay true until we hit this. As soon as we hit that, it'll reset itself, and we'll be ready to go. So what we're doing is we're having different things do different things, and this is what I was talking about, the lab that y'all working on now. Using these instructions right here, you could literally do this with one counter. And what you would do is you would go down and you would use these to set the range when these things happen, right? Instead of having all these different counters. You know? So, well, I guess you could do it with 2 because you got 2 push buttons on different counts, right? Now, we do this a ton of times. Set the limit, set the range, set the range, set the range. And when you find that you do things over, you end up doing the same 2 instructions all the time. Eventually, the people that's doing the programming get smart and say, hey, let's make one instruction where we can put a limit. We can set a range with one instruction instead of what? 2. So, yeah, this is, let's take a break, guys, 2 minutes. This is probably not in your textbook. I know this is something that I added here lately. Sometimes we are only interested in certain bits. So basically, Allen Bradley PLCs deal with words, right? And of course, a word is how many bits? 16 bits. I'm not sure if I'm not sure if 5,000 does. I played around with 5,000 some, but not enough to be extremely versed in it. I'm pretty good in it, but I'm not sure if it deals with the words. It allows you to. In fact, I know it allows you to define what you want to deal with. It's really cool. Allen Bradley Siemens PLCs goes in bytes. So their addressing goes in bytes. Hey, Jalen. We're going to, well, we're doing the Siemens PLCs. If you take the PLC 3 class, we'll go to that. But we're going to go to the Compact Logics. What's that? PLC 3? It's called IoT 212. PLCs and automated systems. How many colleges in the state are teaching that course? In this state? Just this one. But they're not going to show you how to convert a line from Allen Bradley PLCs over there. I don't either. Sometimes when we start dealing with these numbers, we're not interested in some of this. And what we want to have the ability to do is just totally strip them off. Okay. So like me, if we've only got 9 input ports, I'm sorry, we got 10 input bits. Well, if I load in all those inputs using an input port, then that means there's what? There's 6 bits out there that I don't know what they're going to be. I don't know if they'll come in ones or zeros because they're just garbage. So what I would like to have the ability is to get rid of those bits. Okay. So we do this with what we call a mask. So we mask off bits. So we have 2 masks we can use. We can do an AND mask or we can do an OR mask. An AND mask, what you would do is that if I came over here and did this AND mask like this, just for the heck of it, then what would happen is no matter what these bits were up here, they would, in my answer, would have zeros. And then whatever these bits were here, they would come through unchanged. No, it's done with software. What do you mechanically? It's just that. Yeah, they do that a lot on the features that you get in, like in cell phone features, different from this version and that version. Yeah, they've done that for you. They do that in cars. So they put the same engine control module in every car, right? And they put the same body control module in every car. And even wiring harnesses, they use the same wiring harness. You ever look under your hood and find a connector that's not connected to anything? Well, that's because it's the same wiring harness for some option that they have available in their car. But instead of making a special wiring harness for your car, they just make the same wiring harness for the same model. Yeah, and they'll do that all the time. They'll go into these engine control modules and also the body control modules, and they'll just disable stuff that's what that's not you didn't pay for. My wife and my daughter-in-law's got the same band. We got the Town and Country band, and we got the display up there. Well, she can talk on her phone on her display. My wife can't. So she can pair her phone to her display. So my wife can't. So we use an AND mask. We can strip off bits that we're not interested in. So if we AND, so AND means that both. We talked about ANDs, right? So this would be, if this is a 1 and this is a 0. If you AND a 1 and a 0, you get a what? A 1. If you AND a 1 and 0, AND means they both got to be true, right? You understand? So it's just like we came over here and we did this. This is AND. What does that mean? Well, if this contact right here is closed and that contact right there is open, then you still get a false, right? You understand? So what we're saying here is that in an AND mask, to let the bit come through, we're going to put a 1 in our mask. If we want to strip the bit off, we're going to put a what? 0. So this is the mask right here. So this right here would be my unknown. This would be my mask. Who comes up with the mask? You come up with the mask. You're the one that decides what bits. And by George, you could do it in decimal if you wanted to. What you would have to do is you'd have to take your mask, you would have to write it down, you'd have to do that 1, 2, 4, 8, 16, 32, and you'd have to convert it to decimal to enter the mask in decimal, right? It'd be nice if I could enter it in hex, right? So guess what? So what would this mask be in hex? Oh, I'm sorry, we'd go 1, 2. So let me erase it. Oops. I keep hitting the wrong thing. Of course, y'all probably 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So what would my mask be in hexadecimal? It'd be what? 0, 7, F, F. But that would be what? Hex. You see what I just did? Put a little H. So we use an AND mask to clear certain bits, right? To make bits coming through in my answer. So here's my answer right here. So what would happen if I did an OR mask? OR mask says any one will give me a 1. So let's say this was an OR mask. So if this was the 1, this would come through like this, right? And what would these come through? That's ORs. So we can use an OR mask to set bits we want to. We can use an AND mask to clear bits. Does this make sense? Everybody okay? We use AND mask is the predominant. It's the predominant mask we use. Because that's usually what we'll do. We'll load in a input module and we say, okay, I'm only interested in the lower 8 bits, right? You understand? So what can we do? We can just do what? We can just strip them off by using an AND mask. So we could, but we don't want to affect the original number. So guess what they got? They got a, oh, by the way, so we can specify different bases. So even though the processor only understands binary, by default, RS Logic displays all your numbers in what base? Decimal. But the problem is when we start dealing with these maths and stuff like that, it's almost impossible to deal with decimal anymore, right? You understand? So we would like to be able to use what? So if I put a B to the right, what do I specify the number as? Binary. If I put an O to the right, it specifies my number as what? Octal. And if I use an H to the right, it specifies the number as what? Hexadecimal. So we can enter numbers in hex if we want to. So normally these masks, that's what you're going to do. You're going to come up with the binary number and converting it to hex because you don't want to go in and put in 16 ones and zeros, right? To the right. So if I said, you know, if I come up here and I said, you know, 93C5, and then I put an H out there, then that's going to, now you're that's the way you have to enter it. If you want, right. I know there's no H in the hex, so that's why we use the H to identify it as hex. So right here, this says 00008. Yeah, that's exactly what it is. It's like putting this. It's like me putting the subscript. You're exactly right. So what we could do, right? So if I wanted, for some reason, I wanted this mass like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now I could do it in decimal, but what I have to do if I wanted to enter the mask in decimal, what would I have to do? I'd have to go 1, 2, 4, 8, add them all up, come up with a decimal number. You could stick it in there. It's still a binary mask, right? You understand? We enter stuff in decimal, but what does the computer do automatically? Everything is done in binary, right? But it would be nice if I could just do what? Just come in here and go 1, 2, 3, 4. You could do it in octal if you wanted to, but octal is going to be more digits. I go 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. What would this be? Anybody know? And I would just put the what? I just put the H out there. And now I can enter my mask and try instead of trying to go through decimal. So normally we use decimal all the time, except when we're dealing with these masks, right? You understand that? So these OR mask and these AND mask, subnet mask. So even on a subnet mask, you do it in binary, and then you enter it in decimal, right? And luckily on subnet masks, it's not that hard to control. So this is a new instruction. This is called a mask comparison or equal. This is the only thing we got. So what it's going to do is it's going to take this guy, before it compares it, it's going to do what? It's going to match it with that, and then it compares. So this is a really powerful instruction. So we can strip off bits, what? Before we need them, right? That makes sense? And by the way, when you enter these numbers, you can enter them in hex too, right? Does that y'all understand that? Yeah. So move with mask. I'm sorry. Check to see if it's equal, but before it's equal, it does what? It masks it with its AND mask. The MSQ instruction is used to compare whether one source is equal to a second source through a mask. The source and the compare are logically what? And with the mask, then these results are compared to each other. If the resulting values are equal, the wrong state is true. If the resulting values are not equal, then the wrong state is false. So next class, I got a program out there that's got this in there, guys. I'll demonstrate it to you. I think we got one more we need to look at, which means we probably won't get through with the jump instruction for the test. So, because it's time to go to lab. This is the instruction that's been added. So this takes the place of that one we looked at right here. So what they've done, or what Allen Bradley has done, is we use this guy here so often that they did what? They made one instruction that takes care of both that features. So if we want to do this, then what would we have to do? You sleeping over there? Trying to? You sure lay down over there. Well, if we're going to know what I'm saying is that they've taken these two. If we do something all the time, right? You understand? If we have to do something all the time, sooner or later they're going to give us an instruction that does what? That does it, right? Okay. So what do we need to do? We need to have a what? A greater than or less than. But what they're going to do is they're going to put it inside a single instruction. This is called the lim instruction. Limit. So what this does, it runs through that greater than, less than, and it's in one instruction. This is not in your book. It's right up the big top of there. It says what? This instruction is not covered in the textbook. But this is, yeah, they combined it, make a limit test. Yeah. So here at the top, it says you would put what in here. This would be the what? Low limit, right? Down here would be the what? High limit. The lim instruction is used to test the value within or outside of the range. The lim instruction is evaluated based on the low limit test and high limit value shown. What is okay? Yeah, and they're free, guys. Yeah, websites. Yeah. So compare instructions. Lim instruction. Oops, I think I'm gonna have to go back one. Yeah, I'll have to go back one. So the low limit test and high limit values can be word addresses or constant, restricted to the following. If the test parameter is a constant, both low limit and high limit must be word addresses, right? So if we wanted to set a limit, then I could set a what? A low limit. Then I could set a what? A high limit. And if we use two constants, then the test has to be a what? No, the test has to be a. Well, when we came up here and I can't draw on this. Okay. So we came up over a while ago. We came over here and did this what? We came over here and did this, right? And then we set a high limit. I'm sorry, we set a what? This was greater than, so this was a high limit, right? And then that would be backwards. But what are we tested? What was we checking this when we said greater than or equal to whatever? What did we have to specify? So we had an A and a B, right? Okay. And what did we have to specify? So if we said A is greater than B, what did we have to do? I mean, what was we saying? What is A and what is B? A is going to be a number, and B is going to be a number, right? Okay, does that make sense? So down here, what we would do is we would put our range down here. We would say 5, and over here we might have said 10, right? But then up here, we're testing this against, over here we was testing this against a counter, right? Was it a counter? So I would do, if I came over here and put 5, I came over here and put 10, so that would be my low limit and my high limit. What would test be? Well, if I was doing this, then this right here would be my counter. So I'd say my counter has this low limit and my counter has this high limit, right? You understand? Does that make sense? So we could do the same thing that we did. We set, here we were setting our high limit, here we're setting our low limit, right? Everybody okay? Well, what we could do now, here it took how many instructions? 2. But we're comparing it against the same. We were comparing it against the same thing because we were setting a limit. Does that make sense now? So up here we would say we would set our high limit. We would put. I'm sorry. Our high limit would have been what? 10. Our low limit would have been that, and then we specify what we're testing. That makes sense now?